All right, let's talk about how you deal with molarity, units of molarity, all that sort of thing. So molarity, first of all, is another unit of concentration, defined as moles of solute per liters of solution. This is something to be memorized. This needs to be known from off the top of your head. One of the big reasons why is for calculations involved in this, just like with the mass percent, where you want to treat the definition as an equation you can solve for anything, the same is true for this. So we can give you moles and enough information to get moles and liters. You can calculate molarity, or we can give you this and have you solve for this, or we can give you this and have you solve for this, that kind of a thing. So we're going to treat it as an equation that can be used to find the answers to different things. Now, to keep it simple, or rather to start simple, oops, pushing the wrong button there. There we go. What did I put up here? For this question here, this is what the solution looks like. So if we tell you how many grams of something and how many liters of something, the first mistake I've seen people make is they'll take the number of grams and divide by the number of liters and think they have molarity, forgetting that it's not grams per liter, it's moles per liter is the definition. So that means that's the purpose of this thing. You're taking the grams and using the molar mass to convert from grams to moles so that you have moles divided by liters to get molarity. So that essentially is what's going on here. You got to take any masses, convert to moles if you want to find molarity, and then moles, which we calculated before, divided by the number of liters, gives the answer. Now, one might look at this and say, wait, isn't that the wrong number of significant figures? Because 3 sig figs, 4 sig figs, 4 sig figs, shouldn't it be only 3? And the answer is, doesn't matter, it's not the final answer. That's not what you're going to box at the end. This is what you're going to box at the end. So, looking at the numbers used to calculate it, essentially this number and the molar mass, 3 sig figs, 3 sig figs, 4 sig figs. So 3 sig figs determines it to be 3 significant figures. This gets boxed as the answer right here. So, again, we just want to make sure to avoid the most common error, though. Watch your units. You got to make sure if you're trying to find molarity, you got to have moles divided by liters. Common thing that comes up with this, aside from giving you grams instead of moles, what if we give you milliliters or microliters or kiloliters? I don't know, whatever, something other than liters. You would have to convert to liters. This calculation does not work without units of liter on the bottom and mole on the top. So, looking at other ones. Oh, by the way, these are the questions that will be on the homework. Notice, look at that. It's a trick. So you got to make sure to convert this to liters or you can't do anything with it. Anyway, consider this one here, because we can talk about not only the concentration of an overall solution, we can talk about the concentration within a solution of different ions, because we look at this and we say, oh, hey, look at that. This is an ionic compound. We have a metal bound to nonmetals, and beyond that, you can say, look, NO3, that's a polyatomic ion. So anything containing a polyatomic ion is, of course, ionic, which means if it is water-soluble, then when put mixed with water, it will dissociate into ions. Now, from the formula, notice 1 cobalt, and you got to figure out it's 2 plus, because each, so as a reminder, how did you know this? Each cobalt is paired with 2 nitrates, so each nitrate is -1 times 2 means there's a total of -2. That means the cobalt must be a +2. So that's how you would know this and be able to come up with this. But regardless of that, main idea here, 1 cobalt, this 2 means there's 2 nitrates. So that's why you have 2 nitrates right here. That's important, because if you're going to look at the concentration of things, you got to understand for every 1 cobalt there's 2 nitrates. Which means whatever the cobalt concentration is, this has twice as much concentration. Okay, think about that. If there's twice as many nitrates, then whatever the concentration of this is twice as concentrated. Okay, here's how that shows up in the actual numbers in terms of how it would show up in work. How would I want you to show work for this on the test? Because, hey, you could say, oh, look, okay, 0.50 molar of the compound. All right, 0.50 molar of this, and this will be twice as much as this, which is 1.0 molar. Okay, you can say this off the top, you can come up with the answer off the top of your head, but you've got to show your work on a test, so that's the point of this. So you can say, okay, look, this is the molarity And I put it like this just so that you can see how like things could theoretically cancel, even though it doesn't really turn into a big deal. Anyway, this is our given. It's written, it's the first thing you write. And then this comes from this balanced equation, where we have 2 moles of nitrate for every 1 mole of the cobalt-2 nitrate. Okay, so that's where these numbers came from. This came from here, this came from here. So that means essentially times by 2 divided by 1. That's why this answer is what it is. By the way, 2 sig figs makes 2 sig figs. So the question was all the ions, so this would be one of the answers that you box. And the same thing is true for the other one, where, okay, what if we want to find out, this is one of the ions, now here's the other one. So you'll notice a 1-to-1 ratio, that's what this is from. This came from here, this came from here. So this times that divided by that gives the same answer. So that gives us the concentration of both of these. Again, though it may be possible to do it off the top of your head, it's important to be able to show where the answer came from. And that's the function of doing it this way, with your given from there, a conversion factor from the balanced equation, and the answer. All right, so all the rest of these work about that same way. These are examples from the homework. Okay, we can also look at it this way, with this particular example. Now, I remember going through this one with students, and this one is too easy. So I'm actually going to bring up a different version of the same question that was used for another class. And the reason why I say it's too easy, it has a way of making things so that it comes out a little too round. So I think that this other version of it should have what I'm looking for. Yes, this is a different version of the question. This is what I want. So this particular calculation gets at what I'm looking for. The other one, everything came out to be like just about equal, and it was a little too simple, and there were some things that you're forced to deal with here because we're talking moles of silver ions, and now there's 2 silver ions per in each unit of the compound instead of just 1. So this allows us to see the workings of it a little better. So how do you handle a question like this? How many moles of silver ions in 25 milliliters of a 0.75 molar solution? First things first, this is moles per liter. You cannot do anything until you turn this into liters. So, okay, yeah, there's all this. So, like, you're not going to do any calculations until you have converted 25 milliliters to the equivalent in liters. Now, this is getting at another thing. It's saying, okay, if you want to find moles of silver ion, you have to figure out what the concentration of silver ion is so that you can use the concentration and the volume to get an answer in terms of moles, which is what it's asking for. So that's what this was all about here. It says, okay, if we're asked about silver ion, you need concentration of silver ion or else you can't get anything. The question is about silver ion. So that's what we do here. Just like in the previous question, you take this, the given, and then find out how many moles of silver ion are in the given. So there we go. And this is why I wanted this example instead of the other one, because like this turns into like it just gives the same answer and people don't notice it and then they accidentally skip it. So this is an important step, don't miss it. And it becomes much more visible when you get a compound with 2 silvers in it instead of just 1. Anyway, once you have the concentration of the silver ion and the volume in liters, you have everything you need. Now, there's a couple ways to present it. Here's one of them, where I just use it like a unit analysis perspective, where, okay, I have liters, and I have moles per liter. So if I set it up so that liters cancel liters, I've got moles in the answer with 2 sig figs, 2 sig figs, 2 sig figs. That's one way of going about it. That is the answer. This is your final boxed answer right there, though it should technically be in scientific notation. Now, one of the questions that comes up with this is, wait, why do you do it this way? How did you know this times this instead of divided by or whatever? Well, I'll go back and let's look at that. So how did you even know to do this? Let's consider the equation. Molarity equals moles per liter. The question is asking for moles, so just solve for moles. Solve for this. So that means times both sides by liter. So that liters cancel liters, and then you have liter times molarity equals moles, which means liters, this thing, 0.025 liters, it's a terrible number 5, but you get the idea, times the molarity, 1.5 moles per liter of silver ion, equals what the answer was, which I think, what was it again? It was, 3.8 times 10 to the negative second. Okay, this gives the exact same answer as what was animated on the slide. What this is essentially doing is showing you how did you know to take the liters times the molarity instead of divide one thing by another or whatever. Okay, so that is just another case of treat the molarity definition of molarity equals moles per liter. Just treat that as an equation. Figure out what you have and then solve for what you need. It's pretty straightforward that way. And you won't go wrong as long as you're doing proper algebra and solving for what you've been asked to be solved for, like all those sorts of things. If all works out, it's foolproof. So given that, I think let's look at the next type of question, because there's these you can practice with on the homework. So get this out of the way, and then you see up here on the slide it's talking about a standard solution. A solution whose concentration is accurately known. Maybe I'm mixing a known amount of solute with a known amount of water in the volumetric flask. Okay, so put the stuff in, add water, mix it till it dissolves, and then add water all the way up to the line. Anyway, this is AKA, also known as the stock solution. It's like the highly concentrated original solution, and then you can make, you can use water down, you can like pour a little bit of it out and water it up to get what you need. So this is the stock solution is kind of like what you start with. So anyway, I should have said, you write that down, okay, AKA stock solution. So before getting into like watering it down, which I did mention, let's start with this. Actually, maybe I'll leave this out. So this is the answer. Here's the original question. How many grams of solid potassium dichromate are needed to make 1.30 liters of a 0.200 molar solution? What are we looking at here? This is one of a couple ways of dealing with it. So first of all, what we're doing here is figure out how many, you're saying, okay, molarity equals moles per liter. So we need to figure out how many grams are needed. Oh, how do we get grams? The only way to get it is by finding how many moles of the stuff that we need. So that's the purpose of this. Now, how did I know to do this? I go back to this definition of what molarity is and say, molarity being moles per liter, if I times both sides, molarity times liter equals moles. And if I can solve for moles of this, then I can convert moles to grams and call it done. So that's what's going on here. I'm saying, okay, I need to get moles out of this, because once I have units of mole, I can convert moles to gram, and that's it. So here, molarity, or both sides of times by liter to get this version of the equation. Molarity comes from right here, liters from right there. So this is essentially what I'm showing you here is why this happened. Now it's a little opposite order, liters times molarity, but you get the idea, it's the same thing. So it's just 0.200 times 1.30. So that's the number of moles, and then once you have the number of moles, you can convert using the molar mass to the number of grams. Notice 3 sig figs, 3 sig figs, 3 sig figs. Okay, a pattern should be emerging. Every time we deal with molarity, It's always moles. So anytime you get grams, you're either converting to or from moles. So moles, 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 it all involves moles. All right, now I think that should be fairly clear. This would be boxed as the final answer because it was asking how many grams are needed to make that molarity of the solution. These questions have you do a similar thing on the homework. So anyway, what happens in the lab is you mix some number of grams with some number of liters of liquid and you get a stock solution, which is the solution you're starting with. It's usually a highly concentrated original, and then you water it down. So a lot of times you need to add water to a solution to dilute it so that it's easier to work with. And that's what this is all about. If you add water to something, and I think the most common household example would be like bleach. Imagine you don't usually pour pure bleach into your laundry, you water it down. Or you don't clean stuff with pure bleach. The pure bleach will probably dissolve whatever you're trying to clean. You water the bleach down before using it. Likewise, same here. So the thing is, if you add water to something, you're changing the volume because you're adding to the number of liters. You're changing the concentration because it's more watered down, but what doesn't change? Well, the stuff you dissolved, right? It's not appearing or disappearing when you add water. It's just now you have more water in between the stuff that you have dissolved. So we have to understand that when you water something down, concentration does not concentration changes, but the number of moles of solute does not change. So same, changes, changes. All right, obviously copy that into your notes. So the way this looks when you solve it, there's actually two ways to solve it. I'm going to show you one that involves memorizing an equation and one that involves just kind of breaking it down step by step and just using the definition of molarity. Let's do the breaking down step by step, and then I'll show you the equation one. Because moles doesn't change, you have to find the number of moles, and then you can use that to solve the question. So what are we doing here? We're taking, okay, so first of all we're saying, okay, you can't work with milliliters, you gotta convert to liters. That's this step right here. And then, once you have liters, you can say, look, you wanna make this. How many moles are in here? So we take this number, put it here, this number, put it here, because this is what you're making. And you need to know how many moles of stuff need to be in what you make, because you're going to find out how much of this you need to get that certain number of moles. So this becomes the number of moles that you're going to make for, or that you're going to need in the solution. So you need 5. So when you get this number, you then take that number and then use this molarity to find out how many liters of stock solution you need. So we take the moles, and remember, we're just doing this right here. Although in this case, now we're solving for liters, so what do? You times both sides by liters to get this, divide both sides by molarity, so liters equals moles over molarity. So essentially, liters, 0.5 divided by 17.5, the molarity. This is essentially the same thing as doing this. And you get that, and of course, the last thing is it gave you milliliters, so you need to respond in milliliters unless otherwise told. You respond with the same unit that you were given. Now that's one way to do it. Some people like this. Some people find this a little challenging, and that's fine, because there's a second way to do it. It involves memorizing an equation, but if you can handle the equation, the second way is actually easier and faster. Personal favorite of mine. So, other way to do it. If the number of moles doesn't change, you'll notice something. When you take the definition of molarity, again, molarity times volume equals number of moles. So if molarity times volume equals moles, then the number of moles in your original solution, molarity 1, liters 1, equals molarity 2, liters 2. Or instead of liters, we'll say volume, because it's just a more general term. So this gives rise to this, which means you memorize this. So how does this work? The biggest hang up here usually is identifying which molarity is your M1, which molarity is your M2, which is your V1, which is your V2. So one of these is M1, one of these is M2. How to identify? So the answer is, well, okay, well, I suppose there's those, but let's back up a sec. So M1 V1 equals M2 V2. You're going to rearrange the equation and then solve. So let's back up a second before doing that. What am I being asked for? What volume of the stock solution do you need? So I'm being asked for volume. But wait, which one's M1, which one's M2, which one's V1, which one's V2? So number 1 is where you start, number 2 is where you end. A stock solution is what you start with. Your stock solution is always, this is M1. If it's your final solution, if it's what you prepare is what you end up with at the end, the molarity of your prepared solution at the end is M2. And so the volume that goes with this is V2. Anything involving the stock solution is number 1. So volume of stock solution is V1. So essentially, you're being asked to solve for V1. So that's why this I put here, and you want to make sure this is on your handout too. So you're solving for V1, your M1's right there, your M2's right there, your V2's right there. Now here's what's nice. When you solve the equation for V1, like rearrange, okay, we understand that's like divide both sides by V1, divide both sides by V1, so that V1 cancels here. M1 equals M2 V2 over V1. Okay, that's where this came from. Consider what's going to happen to the units when you plug them in. So molarity is going to cancel molarity, leaving units of milliliter if you plug in the units of milliliter, which means your answer is going to come out as milliliter. So hey, as long as you're not mixing different units, you don't need to convert. If you plug in milliliters, you'll get milliliters for an answer. And that part's nice. It saves a conversion step. So personal favorite of mine is this one, but the other method works too. Either one is totally acceptable on the test. You just be aware, we're not going to give this equation. You must memorize it if you plan to use it. So you box that as your answer, because once again, 3 sig figs, 3 sig figs, 3 sig figs, and 3 significant figures. Okay, I think that would be the last thing to mention. This next one, this is one of the homework questions, so you can try it out on the homework and then see if you got it right by looking at the solving method here on the notes which are posted to the website. So that should take care of that. Quick overview of molarity.